this sort of devices, the superconductor terrestrial devices, can be applied to quantum information technology in the future. So this is the status, present status, frequency versus power, emission power. So our IJJ laser, we call lasers, is located somewhere here in the valley, such a sharp valley of the emission power spectrum. This is 1 terahertz, so that we are now working around here, and this is one of the most powerful device to make high terahertz wave. Of course, there are another devices from semiconductor, mostly RTD, and from optics, this is a cascade laser, which is coming down, also similar to region of frequency. But there is some limitation for such sort of semiconducting devices, because if frequency is coming down around 1 terahertz, energy levels is close to the summer energy already, so that you cannot make it. So you have to cool it down anyway. So superconductor, which we are using, we have no problem, this sort of problem, so that we can have more advantage, we think. This is just simply showing the crystal structure and the mechanisms how to make terahertz emission. This is a single crystal unit cell of this called 2212 high temperature superconductor. We have a double copper Watts layer, which was sandwiched in such a way. This is C axis, and making Josephson junction, because in between here it is kind of insulating layer inserted, that is this bismuth Watts layer. So if you apply current along the C axis, you get such sort of IV curve. Current follows, then immediately jumps to normal state, then coming back and coming to the normal superconducting state. But if you have a very small number of IJJ number of junction, you have such sort of beautiful one. But if you have a thicker one, even 1 micron thick, this contains about 760 layers of copper oxide. You have such sort of many branching effect. This one curve corresponding to 1 junction, so we can separate out all those kind of junctions. However, if we go higher current, you have such a back bending, we call back bending, due to heating effect. So this heating effect is nothing but some artificial effect, so that we need to remove this one in order to get better emission. Well, this is just a simple concept to get the radiation. In the case of atom, as you may know from a high school textbook, change of electronic state, electron state from higher to lower, then this energy difference makes photons. And this is also almost the same as for superconducting junction, Josephson junctions. Although superconductor has a gigantic number of electrons, pairs, but this pair can go back and forth in 2 superconductors in contact. Then
recording in progress.
Some light coming out. This coming out frequency is proportional to the voltage applied here. So this is again this junction, which can be written by equivalent electric circuit like this. We call RSJ model, and IV curve according with pendulum. This is exactly the same as the pendulum equation, so that this looks like that. Normal state, then this is phase is rotating and coming back. This is just a simple harmonic like oscillator. So this can be exactly. So this was connected in such a way in a series along the c-axis, so that we think that this single crystal number of junctions looks like that, and the stacking of those layers can be considered as a giant single cross-section junction. And because of the number of layers, about 1,000 per micron thick, and if you have this number, the power emitted due to quantum mechanical effect comes to the number of squared. That means that the power impounds to 10 to 6. So one layer will be something like picowatt, but we can get something like microwatt quite easily by this way. So we call that this coherent oscillation of a set of junctions, like laser. Of course, we set many of them like this, and but we have problems because we send many currents so that this gets heated. So far we could run 3 methods like that and could get it about 600 microwatt by this reference, but not higher than that because of heating effect. So Joule heating is the problem. Joule heating, you can see this is the mesa structure measured by some way to measure temperature of the mesa. So this red part is a hotter part of the mesa. So if you send current, you get such sort of local heating of the mesa, we call hot spot. If you have this hot spot, we have such sort of backbending negative resistance. So this is not good. But interesting thing is, even such a state, we get very strong emission from the mesa. So it is very amazing phenomenon. But anyway, we don't like this hot spot, so that we make this sort of standalone mesa. We remove the base single crystal, and we just make this mesa on top of metallic plate and sapphire below that. So this is a top view of such a mesa, and if we make IV curve, we get very large voltage applied, but of course at certain moment it is broken and get similar backbending state, heating state. But here we get large voltage so that we can go higher frequency. I don't get into this effect. This is so complicated, but it is like that higher current regime. IV characteristics show a strong backbending. This is just what I explained, hotspot effect. This hotspot makes disturbing terahertz radiation. So in order to avoid that, we go low temperature, or we go higher temperature, because if we go higher temperature than 55, we don't have this hotspot effect. But TC is something like 85K, so that it is close to TC. So we have a short distance in temperature in order to get radiation. Here I wrote LSM measurement results, something here. And we have another measurement to get temperature dependent of local heating. We have some disagreement with the experimental results, interpretations, but I don't go into this in detail. So this is just simple way how to show, to make a standalone mesa. We prepare such sort of sample and we cut it, and we put it on a plate. It's very simple, but small size, so that it is rather tedious process. Or we can just etch by edges. Then we ion mirroring, and we mirror through micron thick. Then we just take this out by dissolving this grease. Then we get such sort of small mesa, many of them, and we just put it on the gold plate. Then we can make attachment. So this is another way to make a device. So sapphire 2 plate, we make a gold plate like this. Then we insert inside such sort of small standalone mesa. Then clamped like this device from top and bottom. Then you can simply make very nice way. There is another effect for the radiation, that is cavity effect. The mesa itself works as a cavity for the resonator of emission. So this can be considered to be parallel plate superconductor, plus, of course, Cooper pairs inside. So we cannot neglect that, but we can get most of the effect from this parallel plate model. So this is a we call patch antenna model. 2 plates in between, some dielectric material inside. In fact, superconducting material inside. But we can simulate what kind of radiation can be emitted from this. So there is a resonance mode inside. So we tried many of them, rectangular or square or circle disc or triangular or isosceles triangular or some funny shape. But anyway, any kind of geometrical shape have a certain resonance frequency so that we can calculate it, in fact, quite detailed. So we can predict what kind of resonance mode is emitted from this sort of method. So how to make higher power? So that we are now considering parametric amplifier, we call PA. This is so far very well known since a long time ago. Mostly mechanical or electrical way used before. But this is also used for superconductors because superconductor Josephson junction is nonlinear, so that using this nonlinear effect, we can make this parametric amplification. So Josephson junction is the most a beautiful example for making this parametric amplifier. So there is already examples. Here I should just show you the two pendulum seriously connected, how it behaves. If amplitude is small, two simple harmonic oscillator are connected like this, and it is quite easy to understand. And if you have a larger amplitude like this, then you have a very complicated phenomena, and you cannot predict what's going on here. This is kind of chaotic state known. And this is something like thousands of harmonic oscillators connected seriously, and we are now in such a state so that we are very complicated situation in this Josephson junction, you can imagine. So parametric amplifier, this is just a simple cartoon to explain as if it's a swing for children. You go like this, and you can go larger amplitude by just standing up, twice frequencies of this thing. This can be exactly mapped to electric circuit like this, the variable capacitor, variable inductors. So those are mechanical, but this is electrical and similar. Similarly, this can be applied to Josephson junction. In this case, linear traveling wave parametric amplifier is already used for this. reference. And this is Josephson junctions used for read out of the uh, quantum computing signals. So we are now considering such sort of design of emitters. We have two-stage disco method. One is larger method below, and on top we put smaller size, but half size of that, so that we have twice higher frequency at upper part and low than the lower part. So if we drive this upper part, then we can induce parametrically this lower frequency, half of frequency terahertz. But there are some sort of questions whether it is better to put such sort of aside or in the middle of this plate. We don't know which is better. We are now just started to make such sort of junction to test whether this works or not, but still we are not yet sure which is better. Maybe both works, or maybe one of them work. I don't know exactly, but this is the thing which we are considering. Another arrangement is just to put the two of them in a row beside of this larger one, a small one like this. Then couples two of them by electromagnetic way and induce parametric effect. And this may also work. Maybe we can arrange those one in different patterns, more, not only two, but 3, 4 around. This is, we are now trying, and few of them already known, it's couples and emit strong radiation, but not parametric way, so that we are now trying to find out the effect, parametric effect, just to restart this to work. Another interesting way to make higher power is using a photonic crystal effect. So we use such sort of, for instance, array of hole in this case. This is gold, same plate, and we have many holes in such a way. This is the hexagonal way. If we put the emitting device like this, then this wave comes in to the center, and it is photonically enhanced because of the cavity resonance effect, high Q effect. So we are now designing such sort of simulating by computer what kind of arrangement of those sources and what kind of size of the hole or size of the patterns, so on. And of course, some case you can see such sort of high Q dot effect. So this photonic laser can be constructed by making arrays of IJJ around this. Oh, well, this is only the now simulation and consideration and not practically done, but we are now trying to make it soon. So we have lots of possibility now to make many devices out of this sort of technologies, nanotechnologies, recently developing photonic crystals, and also parametric amplifier effect. So I like to conclude my talk For high power terahertz emission, we are now aiming at 1 milliwatt at least, or maybe higher than that, from my meso structure. Hopefully working at nitrogen temperature using high temperature superconductors. And this is coherent radiation, so that it is like a laser beam, so that it is easy to use for other purposes like quantum computing and reading out of signals, so on, in the future. So those are very hopeful fields to work in the future. But still, we need to go many things. And these technologies provide us with much wider future applications in the field of terahertz device, certainly. And one of them is, of course, quantum information technologies to be integrated in. This will be our ultimate goal. Thank you very much.
Sorry, there is probably a delay, so.
What's the limiting factor?
Well, it's a good question. We don't know. That is about well, less than 1% normally, or 1% or so. I think if you think of this as a kind of a quantum mechanical device, normally, you know, like LED laser, so what power range. So we hope still can go higher power.
Oh, okay. Thank you.
Yes, thank you.